Okay, class. Welcome to this next lecture of memory organization. Today we are going to talk about a special type of memory called the cache memory. No, it is not the cash that we can spend in lieu of or instead of the cards or digital payments. This is actually CACHE, cache memory, but we also pronounce it like cache memory. Now, cache memory, as you might remember from the memory hierarchy diagram that we have discussed earlier, has the highest speed after the CPU registers. And obviously, as it comes in the memory hierarchy quite high, just below the registers, it means that its size is also small, the cost is also quite high, and the speed is obviously high. As you can once again see in this diagram, this memory hierarchy depiction that I've shown, that cache memory comes just below the registers. And if you see this table, you'll be able to understand that the cost of the cache memory is quite high, the speed is quite high, and the size is quite low. Right? Let's understand how the cache memory actually works and why does it come just below registers. Why is the cache memory needed and why is the cache memory so fast? Now, cache memory is needed because there is a principle called the principle of locality of reference. According to the principle of locality of reference, the data or the instructions that are required by the CPU together tend to exist in the memory together. What it means is, if the CPU requires two pieces of information or two pieces of data simultaneously or sequentially, there is a quite larger probability that the two pieces of information will be present in close by memory locations. So this cache memory, it is a small, fast memory which is placed between the CPU and the main memory. Now, what cache memory tries to do, cache memory tries to anticipate the needs of the CPU. Cache memory tries to anticipate the needs of the CPU. What it means is cache memory tries to guess what will be the next data that will be required by the CPU or what will be the next instruction that will be required by the CPU. Now what happens is the data which is more probable to be required next by the CPU is brought into the cache memory. And when the CPU requires that piece of information, it is delivered from the cache memory to the CPU at a much higher rate. Why? Because the cache memory is faster because of the way it is manufactured. So when a program is executed, the cache memory is searched first. Whenever the CPU wants to access a piece of information, it will first access the cache memory. If the information is available in the cache memory, it will read that information from the cache memory at a higher rate, higher speed. And if it is not available, only then it will go to the main memory. As I said earlier, when a program references a memory location, it is likely to reference the same or a nearby memory location again soon. Right? This is what is meant by the principle of locality of reference. The locality of references essentially can be of two types. One is the temporal locality and one is the spatial locality. Right? Let's go through this once. The reference to memory at any given time interval tends to be confined within a localized area. If you think about it, if I talk about, let us say, the locality of reference of instructions, see, the CPU tends to read both instructions and data from the main memory. If I talk about the instructions that will be read from the memory sequentially or close to each other will be the instructions that make up a program. And the program tend to be stored in the program instructions tend to be stored in continuous memory locations. So obviously locality of reference works over there. The various instructions that are making up a program tend to be stored together at a particular memory, starting at a particular memory location. Similarly, when you start working with a program, when you keep on reading and writing data, what happens is the data that is required together or in subsequent instructions, they also tend to be focused or they also tend to be stored in nearby memory locations. Temporal locality basically means the information which will be used in near future. Temporal is related to time. What it means is that suppose I have accessed a particular instruction or a data, piece of data at this point in time. Now the instruction that I will be requiring in the near future. See, here is a time element over here. The information which will be required in near future is likely to be in use nearly, right? So for example, loops. Spatial locality means the locality in space. The data or the piece of information that is required now, there is a higher probability that the data that will be required subsequently will tend to be stored near this piece of data. So these are the locality of references which the cache memory actually uses in order to speed up the operation of the CPU. Now, why is the cache memory fast? Let us once again reiterate. A cache memory is fast, number one, because it is closer to the CPU as compared to the main memory. As I already said, that cache memory is placed between the CPU and the main memory. So obviously it is closer to the CPU, so it will be fast. Second, it is smaller in size. So that means there are lesser number of locations from which the CPU needs to find the particular piece of information, and lesser the number of locations where the CPU has to search. That means the search can be performed faster. And the third point being that the CPU is configured, oh sorry, the cache memory is manufactured by special electronics which give you a faster rate of data transfer. So let's once again just to recap, what is a cache memory? A cache memory is a high speed memory which is placed between the CPU and the main memory. The task of the cache memory is to anticipate the requirement of the CPU. Means the cache memory tries to anticipate, tries to guess what data or instruction will be needed by the CPU next, and that data or instruction is brought into the cache memory beforehand. What it means is whenever the CPU will require that piece of data or instructions, first the cache memory will be searched. If the information is available in the cache memory, it will be read from the cache memory at a high speed. And if it is not available in the cache memory, then it will go to the main memory. Right? So the first scenario or first condition or first situation where the information that the CPU requires is present in the cache memory is called a cache hit. I'll repeat, a cache hit is a situation where the information which was required by the CPU is available in the cache memory and it will be transferred from the cache memory to the CPU at a higher rate. In case the information that is required by the CPU is not present in the cache memory, this situation is called cache miss. So in this case, the data is brought from the main memory into the CPU. There are two possibilities which we'll talk about in detail later on. At the same time, when the information is being brought from the main memory to the CPU, it is also placed in the cache memory. Why? Because of the principle of locality of reference, there is a quite high probability that the subsequent instructions or the subsequent data which will be required by the CPU will be occurring close to this piece of information. Now, we may have a unified cache or a split cache. A unified cache is where the instructions and data share the same cache. Split cache means we can have a different separate cache for instructions and separate cache for data. Now, there are different types of caches like level 1 cache, level 2 cache, and so on. Level 1 cache is present on the CPU chip. Level 2 cache is present on the motherboard. It is present in between the unified cache or split cache which is present on the CPU chip and the main memory. Now, we may also have external cache devices, but we'll not be talking about those external cache devices over here. Right. So we use memory to speed up the operation of the CPU. Right. Now, Let's talk something about the performance of the cache. But let me recap once again. Whenever the CPU requires a piece of information, it is first searched in the cache memory. If it is available in the cache memory, then the data is read from the cache memory. And if the data is not available in the cache memory, then CPU goes and searches in the main memory. Pay attention. While reading the data from the main memory, the data is simultaneously copied on the cache memory, right? So the data is simultaneously copied on the cache memory. Another very important piece of information: whenever there is a cache miss, the data that is brought from the sorry, main memory is not just the piece of information which was required by the CPU, but we read an entire block of data from the main memory and put it in the cache memory so that the nearby locations can be accessed readily if required. Now, let us say that the TM is the main memory access time. TC is the cache memory access time. If we have a system which has both a main memory and a cache memory, now let us see how we can find out the effective access time. Now, if you see, we have something called the hit ratio. Hit ratio is the percentage of all the memory accesses by the CPU or all the data accesses by the CPU which are located within the cache memory. That means, say for example, if the CPU starts or if the CPU performs 100 data searches, and out of those 100 data searches 80 data searches can be fulfilled by the cache memory, then the hit ratio will be 80 divided by 100, that is 0.8. So this is hit ratio. So the effective time is H multiplied by TC plus 1 minus H TM. Just think about it. This is again the percentage of accesses that the data is obtained from the cache memory. So obviously data is obtained from the cache memory at the access time TC. And this is the percentage of those accesses where the CPU has to go to main memory. So this is the main memory access time. See, this is a simple example. If I take TC to be 0.4 microseconds, TM to be 1.2 microseconds, and H to be 0.85, then the effective time is 0.52 microseconds. As you can see, the 0.52 microseconds is approximately or a little bit less than the main memory access time. So this is how we measure the performance of the cache memory. Now, before we proceed any further, let's clarify a couple of things. Main memory is divided into a number of blocks. Now, I would suggest you take out a pen and paper and jot down certain things as I tell you, right? Main memory is divided into a number of blocks. Cache memory is divided into a number of blocks. To segregate or to clearly differentiate, we call the blocks of cache memory as lines. So we say that main memory is divided into blocks and the cache memory is divided into lines. Very important point. Size of a main memory block is exactly same as the size of a cache memory line. What it means is, say for example, your main memory is divided into a 1 kilobyte blocks. Let us say the main memory is divided into blocks and the size of a block is 1 kilobyte. Then the cache memory that you will be using will also be divided into lines and the size of those lines will also be 1 kilobyte. What is different is the main memory will have a much higher number of blocks as compared to the number of lines in the cache memory. As we have already discussed that the size of the cache memory is quite small as compared to the size of the main memory. So let me repeat, main memory is divided into blocks, cache memory is divided into lines. Size of a block is equal to size of a line. But the number of blocks is much higher as compared to the number of lines. Now what happens is whenever there is a cache miss, that means the data that is required by the CPU is not available in the cache memory. At that time, the CPU goes to the main memory and reads not just the piece of information which was required, but the entire block. That entire block is read from the main memory, and that block is placed in the cache memory, and a piece of information which was required by the CPU is provided to the CPU. So one complete block of data comes into the cache memory so that whenever the CPU next requires a piece of information, it can be read from within the block, if it is present within that block, from the cache memory. Now let's proceed. This is it another example of the cache memory calculation. So if TC is equal to 160 nanoseconds, TM is equal to 960 nanoseconds, and H is equal to 0.9, then this is the effective time. You can find out the efficiency like this, right? Efficiency is obviously TC upon TE. This is the efficiency of the cache memory, right? So let's see this flowchart. It basically talks about the reading of data from the memory and the cache memory. Now, there are two basic issues that are related to using a cache memory, right? Say, begin. The processor outputs the memory address A. Once again, I want you to note it down. The CPU will always generate the memory address of the larger memory. This is a very important point. The CPU will always generate the memory address of the larger memory. Now in this case, main memory is larger and the cache memory is smaller. So the CPU is going to generate the address of the main memory. But it will go and search for the piece of data in the cache memory. Now this is a problem. The address that is being generated is that of the main memory. Now please we should try to visualize this. Suppose your main memory has, let us take a simple example, 128 blocks or 128 words that are stored in it. 128 words stored in the main memory mean that the CPU will generate a 7-bit address. 2 to the power 7 is 128. Now let us assume that the cache memory has only 32 words stored in it. Obviously it is smaller than main memory. So if the cache memory has 32 words stored in it, that means the cache memory needs a memory address of 5 bits. But the CPU is generating a 32-bit address, sorry, 7-bit address, but the cache memory requires a 5-bit address. So your first problem is how to map that 7-bit address into this 5-bit address. Second, and a very important point, as I said that the cache memory is smaller as compared to the main memory. What happens if the cache is full? Say you are trying to read some data from the cache memory and it is not present in the cache memory, a situation which is called the cache miss, and you want to read the data from the main memory and simultaneously bring the entire block into the cache memory, but the cache memory is full. Now what do we do? Now because of locality of reference, we know that the subsequent pieces of information that will be required will be nearby this new address. So we need to bring this new block into the cache memory. That means it necessitates removal of some old blocks from the cache memory. Now we need some replacement policy for that. We'll come to these two things later on. So the processor outputs the memory address A. First of all, we will try to find out the memory block B that will contain the address A. Now, we are not saying that this particular block will be present in the memory or cache memory. I am just identifying the block which will hold this particular address. Next, we will check whether the block B is present in the cache memory. If it is present in the cache memory, all is well. You will simply read the data from the cache memory and supply the word at address A to the processor. But what if the data is not present in the cache memory? Now here, as you can see, this arrow indicates that trying to find out whether the particular block is present in the cache B uses a mapping function. What is mapping function? We'll come to it later. It's quite a extensive topic. We'll come to it in the subsequent lecture. So if the data is not present in the cache memory, then what we'll do? We will initiate the reading of the data from the main memory. Right? Now, when we try to read the data from the main memory, again, we will assign a particular cache line to this main memory block. Why? Because once I'm reading the data from main memory, this block will also be copied on the cache memory. This again requires the mapping function. Now again, here again comes a condition. There might be two cases. The particular cache line where this memory block is to be copied, it can be full or it can be empty. If it is free, again all is well, no problems. Supply the word at the address A to processor, put the data into the cache memory, and that's all. But if it is full, then I will have to use some replacement policy that might be designed or defined earlier. There are a number of replacement policies. I'll again give you a brief idea about those replacement policies later on. So I will have to use a particular replacement policy to free this particular memory, this line of the cache memory, before I can bring in the data from the main memory. So this is the entire process of data reading from main memory with cache memory, right?